Industrial processes used in the manufacture of everything from food to fashion to pharmaceuticals contribute to climate change and often rely on harsh chemicals that can pollute the environment. I'm Russell Beard in the Arctic, where a team of scientists think that the secret to reducing the environmental impact of industry and decreasing our dependence on fossil fuels might just be found in fungi. But this story starts 1,000 miles away in Copenhagen, Denmark, where the biotech company Enzymes has its headquarters and research lab. Top mycologist Sarah Landvik in Macaco Sasa work on the production of biological microorganisms. Macaco, hi.
Hello.
Hi, how are you?
I'm fine, thank you.
Don't want to get lost. This place is massive.
No, you will get lost. We are dealing with live microorganisms. Yes,
Yeah.
we are, especially bacteria and fungi.
Over the last 2 decades, Macaco and Sarah have been growing a library of thousands of microorganisms that produce enzymes. These biological catalysts kickstart chemical reactions in the cells of all living organisms. One of the most diverse sources of enzymes is to be found in fungi. What would the world be like if there was no fungi?
We would just drown in organic material. We would just drown in all the leaves and the wood and the twigs that the forest shed. These are what we call wood-degrading mushrooms. So
Okay.
you may have seen in the woods and forests a mushroom like this growing directly on huge logs, which have already fallen and are dead.
Yeah.
And they sit there using their enzymes to degrade the cellulose in the wood.
Man has used enzymes found in fungi and bacteria for hundreds of years, from the yeasts used in making bread and beer to present-day washing powders and even fashion.
To achieve this, this light blue color of denim, you either used brimstone and damaged your washing machines, or you used chlorine to bleach the dark blue into a lighter blue color, right? Now this can be done using cellulases. So enzymes can be used in all sorts of applications where we today maybe use harsh chemicals, and we might try to substitute those with enzymes instead.
So once Macaco and Sarah have found the enzyme that they think has the most potential, it comes here to the House of Protein Engineering to be optimized for industrial use.
Come in.
Thanks for having us. Leonardo de Maria works at a molecular level to make enzymes tougher and more resilient to the harsh environment of industry.
No, if you think about a marathon, right? So nature has run 42 kilometers, and we are doing the last 200 meters.
Okay.
Proteins are chains, and they are made of amino acids. And there are 20 amino acids you can pick to make a chain.
Only 20?
Only 20, the natural amino acids.
Despite there being only 20 building blocks, the combinations of these amino acids are practically infinite.
A lipase is 269 amino acids long.
Wow, look at that.
So I can start to imagine what if we change that one there to something smaller or bigger, right? Would it take me to what we think will make it a better enzyme in the application? For example, if we have an enzyme that we need to push it to work at slightly higher temperatures than the temperatures that nature has made it to work. Then what I can do on the computer is to boil the enzyme and then see how it breaks. Then I can again focus in those regions my suggestions, some of the other 19 possibilities we have to play with, right? And make it stiffer.
Do you think this is growing? Do you think that there's going to be many more people around the world interested in this science?
I think so. I'm trained as a physicist, right? And we could say that physics was the science that dominated last century, but biology will dominate this century for sure.
Enzymes are now used in everything from big pharma to biofuel. Potentially any process that depends on petroleum-based chemicals can be replaced with a biological enzyme. At the Kalundborg industrial facility, enzymes are produced on a massive scale.
Here is the production strain that has been developed through the work in R&D. So I will now give that to Louise.
And this is then just exploded into huge amounts.
There we go.
obviously important to sterilize everything here, because what they've created in here is the perfect conditions for bacteria and microorganisms to thrive. So obviously if it is contaminated by just one rogue bacteria, it could contaminate the whole batch. And how long will it take before this tank is full?
About 12 to 48 hours.
Is that all? Wow.
Not only do these enzymes replace chemicals in industry, they're also reducing the temperature that industrial processes are conducted at. This simple reduction in energy use is having a huge impact on CO2 emissions. The new generation of biological washing powders contain enzymes that allow clothes to be cleaned at just 20 degrees Celsius.
If you work out how much carbon dioxide you can save by washing at the lower temperatures, if everybody in the EU did it with the population of 500 million, we'd save 30 million tons of carbon dioxide a year.
Novozymes now produce hundreds of thousands of tons of enzymes a year and estimate that in 2012, the use of their products saved 48 million tons of CO2 emissions worldwide.
So each one of these bags is a ton of enzymes.
But Novozymes aren't the only players in this emerging market. With increasing competition to develop new products and applications, it's down to Makako and Sarah to travel further afield in search of fungi that will work at even lower temperatures and have an even greater impact on climate change.
Right now we are above the Arctic circles. Very soon this area will be covered with meters and meters of snow, and it will be very, very cold. So obviously all of the plants and animals and mushrooms that we find in this type of environment are able to tolerate very low temperatures, and that is what we are interested in. Wherever there's water, there are mushrooms. So you can see it's growing directly on the moss, where it's the conditions are humid. So these are mushrooms that do not actually degrade organic material, but they grow in a symbiosis with a host tree. So this may be the tree that it is associated with. The association takes place beneath the ground, of course, where the mycelium of this fungus is in direct contact with the rootlets of these trees. So the fungus is transporting water and nutrients to the tree, and the tree is giving back carbohydrates.
So this network of mycelia or hyphae, is this all part of the same organism? Is that what we're looking at there?
It could be. What we see is not always what it is, but we know that one and the same fungus can be spread out over a huge area. And the biggest known one is in Oregon, and that is an Armillaria. And that one is known to exist over an area of 3.5 square miles.
3.5 square miles, the same organism?
Same organism.
Wow. As an organism, fungi are more like animals than plants, and it's their ability to adapt and survive that makes them one of the most prolific organisms on the planet. In fact, in 1 cubic inch of soil, there could be more than 8 miles of mycelium.
And it's amazing, you know, just to the naked eye, it looks like quite a barren landscape. We're obviously very exposed up here. But when you see it through their eyes and you get up close, you realize that actually it's incredibly diverse. All kinds of things there, just at your feet. But we better catch up with them. I don't want to get lost around here. Now, Makako, let me help. I want to find a fungus.
Yeah?
Give me a mission. You said that next to the rivers is a good place to find fungus. Wherever we find water.
Wherever you find water, you will find fungi. And they can be very small, so you have to use your eyes.
So what about these black spots on these leaves? Could that be a fungus?
Yes, that could easily be caused by a fungus, yeah.
They kind of just look like black dots. Ah, oh no, it's a snail. We found one. There you go.
Oh, very nice.
Okay.
Yeah, you can see what it looks like, right? You can
it's
see
got
that
hairs.
it has hairs.
It's a hairy fungus.
Yeah.
That's a win. Cool.
We will bring it back and look at it.
Put it in the treasure box.
This way.
Let's smell it.
Do you ever think you like fungus too much?
But you can never like fungus too much.
Don't think that.
Can you?
Cannot like. If we find a fungus with an enzyme that we can use in any industry, we have the possibilities and opportunities to combat the climate changes. The enzymes are there as they were before. We just need to utilize them in different ways.
So that's where we're heading?
Yes.
Yeah.
Right to the top?
Yes.
To the top.
Okay. You really understand how these glaciers have the force to carve the landscape as we know it. All of these mountains, all of these valleys have been carved by glaciers like this.
There are many microorganisms everywhere, right? That's what I've been trying to tell you.
Wow.
So we will try to take some soil samples right by the ice. All of this debris, all of this organic material has, after all, landed here. So somebody has to start degrading this stuff.
The hope is that the enzymes produced by the microorganisms adapted to function in the mud and meltwaters of this glacier might have the potential to decrease the energy use of industry and help rebalance our impact on the planet.
I'm sure that we'll find some spores that we can isolate from there, and hopefully they will germinate and we can screen them. Yeah.
And all the work that's gone into that, I mean, on nature's behalf, that's brought it here, it's almost like there's been millions of years of R&D already gone into it, even at this stage.
Yeah, definitely. It's been going on for many, many years. Yeah, exactly, yeah. It just doesn't take place overnight. If you think of biotechnology, it all starts here in nature. It's difficult to say when enough is enough. We find and bring back whatever we can, whatever we think is interesting, and anything that is useful in our lab, we will bring back and study and screen. So no, it will be an endless adventure.